It's 9 o'clock and we've got one student attending. I have to start on time today because I have to end on time today. I've got another meeting that starts at 11, so I've got to get finished. Well, if I don't get finished, then what I'll do is just stop the video, end the meeting, and then after my other meeting, I'll come back and finish the video. But I hope I don't have to do that because I want my students to be able to ask questions in the process of recording. All right, so I'm going to share the PowerPoints for, here we go. And there. And let's start the slideshow. Okay. So we're into Exam 2 material, which will include Chapter 4, 5, and 6. And this chapter in particular and Chapter 5 focus on bonding. And in the process of describing what a chemical bond is, we're also going to learn how to name compounds. So just a heads up. All right, so Chapter 4 is focused on Ionic Bond model. But we're going to introduce other concepts along the way. It's just impossible to separate one from the other. And you'll see what I mean as we progress. That's just an outline of the chapter. Okay. In the simplest terms, a chemical bond is the name for the attractive force that holds atoms together. And when we say it holds them together, it allows them to change their character and identity based on their association with other atoms of the same or different elements. Now, I've mentioned before, and I'll say it again, when two atoms come together, the first thing they see is electrons. So the bond is composed of that interaction of electrons in the outermost shells or orbitals of those approaching atoms. The bonds can be divided into basically two types, and this is a this is a construct, a human construct, so that we can try to understand what the bond is about. The Ionic Bond and the Covalent Bond. Those are two major divisions. The Ionic Bond is formed between two atoms that have become ions. So electrons have been transferred. And you have a positive ion and a negative ion, and they attract. It's purely electrostatic. The covalent bond, on the other hand, is a bond in which electrons are shared. In other words, if two atoms approach, neither one is strong enough to attract electrons away from the other one. So they settle on sharing. And as a matter of fact, the covalent bond is stronger than the ionic bond. Okay. Excuse me. In the sciences, we tend to go for years, decades, accumulating information. So we subdivide our topics, and individuals work on various parts of those topics. Occasionally, a mind will open that can synthesize all that information into a coherent explanation or model of what's actually happening. Linus Pauling was one of those minds, and he won a Nobel Prize in 1954 for his efforts in explaining the nature of the chemical bond. In fact, he wrote a book about it. All right, here's the ionic bond. And like I said before, it's simply a transfer of electrons, complete transfer of electrons, one or more, from one atom to the other. And when you do that, you lose electrons from one and you gain electrons by the other. An example, table salt. Well, that one's not working too well. Hold on a second. Let me try one of these. There we go. Sodium and chlorine. What happens is sodium will lose an electron. It's a metal. Metals like to lose electrons. So one electron is transferred to that chlorine. So what happens is if you lose a negative charge, that makes an excess of positives. Right? Positives are based upon the number of protons. So sodium will have 11 protons. And if it loses an electron, now it only has 10 electrons. So that gives it a plus charge. This electron transferred over to chlorine, which has 17 electrons when it's neutral, will gain an electron. Now it has 18 electrons, and that gives it a net negative charge. Now the attractive force here is purely electrostatic. This is called a cation. This is called an anion. And the cation attracts the anion based upon electrostatic attraction. The covalent bond is a sharing of electrons. And these types of bonds are formed between two nonmetals. So, for instance, I think of a good example. Let's just say we've got two oxygen atoms. Okay. Those oxygen atoms have 8 electrons. But one of those electrons, and we'll get into that in more detail in just a minute, one of those electrons is unpaired. In other words, it doesn't have a neighbor. Remember our electronic configuration, sometimes we end up with electrons in shells that don't have a neighbor. They're not paired. Well, that's the case here. What happens is, with two oxygens, neither one is strong enough to attract an electron away from the other because they're both the same. So what they do is they share those two electrons and they form a bond. Well, actually, they form two bonds. And we designate those bonds with a line between them. And each line in the bonding notation represents 2 electrons. Okay, so those are shared electrons. They spend time equally between the two. Okay, like I said before, this construct of ionic versus covalent bonding is so that we can wrap our minds around what's actually happening. Like I said before, nature just does what it does. It's up to us to try to understand it, and these are the ways that we do it. But when we describe an ionic bond versus a covalent bond, some are nearly 100% ionic and some are nearly 100% covalent. But a great many of them are somewhere in between. The bonds have some ionic character and some covalent character. Right? So it's a continuum. All right. Another concept that's important and helps us determine how bonds form is to recognize that all electrons surrounding an atom do not participate in bonding. Just the outermost electrons, those that are encountered first when atoms approach. These electrons are called valence electrons. And remember when we wrote our electronic configuration, well, let's take oxygen again. Right? We would write the electronic configuration like this: 1s2, 2s2, 2p4. Okay? The valence electrons are the ones, all the electrons that have the same principal quantum number, that 2. Okay? If we had an atom here that was described with 3, we would go to the highest energy level and work our way back with that number. So here we have 6 valence electrons. If we were to go to chlorine, right, we would have 1s2, 2s2, 2p6, 3s2, and 3p5. Let's see, 2, 4, 10, 17. These would be the valence electrons. Okay? Now, when we get to those examples where you have switching, right, where you have the 3s ahead of the 4s, you would still stay with that principal quantum number. The highest principal quantum number determines which electrons are candidates for valence. One other thing that we notice about the periodic table and the way it's structured is it lends itself to the concept of the octet rule. Octet means 8 electrons. And if an atom is constructed with 8 electrons, then it becomes unreactive. And that's the case with noble gases, right? So neon would have 10, right? And it would have 1s2, 2s2, 2p6. 8 electrons. Now this works pretty well for the second and the third period, because between one side and the other, right, second and third, from one side to the other, you don't have to cross through the transition metals. As long as you're in the second and third period, first period I'll talk about in a minute, you're going from 1, 2, 3, 4, 5, 6, 7, 8 to neon. So each one, as you go from left to right, just add a valence electron. So lithium would have 1 valence electron, beryllium would have 2, boron 3, carbon 4, so forth, all the way across. Now you can still count those octets when you cross over the transition metals, elements and count your valence electrons that way. But when you do that, you have to recognize that once they get into a reaction situation, these d electrons can become active. All right, so that's why this octet rule works best for the second and the third period. Now the first period only has 1s, right? So it goes by the duet rule. a full valence shell for hydrogen and helium is just 2 electrons. Okay. Oh, and by the way, when you have the octet rule is useful for determining how atoms will bond. What they try to do is satisfy the octet. If it's an ionic bond, they'll satisfy the octet by taking electrons and giving up electrons to complete that electronic configuration that looks like a noble gas. If they're sharing electrons, then they will share enough electrons so that they can feel as if their octet is satisfied. And we'll talk about that a little more as we progress. Okay, there's the valence electrons. And like I said before, you generally focus on the S and the P subshells, which means second and third period are best candidates for the octet rule, because they only have access to S and P orbitals at that point. Okay, another way to help us, and this is a natural progression from the concept of the octet rule, was the introduction of Lewis dot structures. Lewis was a master chemist, and he proposed writing chemical symbols in a way that you are only interested in that octet of electrons. So he would surround his symbols with dots representing those valence electrons. So we'll go back to oxygen. That has 8, 1s2, 2s2, 2p4, right? You have 6 valence electrons. So what you would do is you would write your symbol and you would start populating electrons like that. Okay, we've used up 4 of them. Now we need 2 more. So now we have to start pairing them up. So that would be a Lewis dot structure for oxygen. 2, 4, 5, 6. And then when they come together, like that, you notice that the unpaired electrons are the ones that want to bond. And those 2 pairs form the bonds. Now, what does the oxygen think? It thinks it has 8 electrons, right? 1, 2, 3, 4, 5, 6 for that one. 7, 8, excuse me, 7, 8. So it thinks it has 8. This one thinks 1, 2, 3, 4, 5, 6, 7, 8. Thinks it has 8. It doesn't really have 8, but by sharing, they satisfy an octet valence shell. Okay, these are examples, right? So notice that we're only dealing with the first 2 groups and the last 6 groups for this octet rule to work. And notice that from left to right, lithium has 1, it's in the first group. Beryllium has 2, it's in the second group. Right? So you can count how many valence electrons there are depending on how far from the left you move over. Beryllium is in the third representative group. Right? That's the value of the earlier numbering system for these columns, for these groups. Roman numeral 2A, 1A, 2A, 3, all the way up to 8A, indicates that the valence electrons you have in there are equal to that Roman numeral. So fluorine would have 7. Chlorine would have 7 also. Okay, so let's see. How many valence electrons are in each of the following elements? Well, calcium's in the second group, so it only has 2. And if you look at your periodic table, you know where those belong, right? Calcium's right here. Calcium right here. It's in the 4th period, and it's in the group that is filling s orbitals. It's the 2nd group in that region, so it has to be 4s2, right? So you can write the electronic configuration. I think I've said this before. If you know how the periodic table is constructed, you can write the electronic structure if you just follow the periodic table and where those electrons are located. Like this is the S group, that's the P group, this is the D group, and this is the F group. Right? And those are the orbitals that are being filled when you write that structure. Selenium. Right? Selenium is in the oxygens group. It's a chalcogen. So it has 2 S's, and then it has 4 P's, because in the P group, it's 4 to the right. The S orbital's already been filled, but it's in the 4th period. So it has a 4s2 and a 4p4. Carbon. Carbon is in the 2nd group. So it's going to be, and it's 4 to the right. So the first 2 are going to be S's, right? Right, so it has 2s2 and then 2 more in the P group, 2p2. Those are your valence electrons. Those are the electrons that are available for bonding. All right, and these are just statements of the generalities that I've already mentioned. These representative elements, if they're in the same group, they have the same number of valence electrons as their neighbors, above and below. The number of valence electrons is the same as the Roman numeral in the periodic table. If your periodic table doesn't have Roman numerals built in, some of them don't. They may have the new system, 1 to 18 from left to right. Then just count left to right. The first 2 groups are S's, and then if you have to, skip over the transition metals and then start counting again in the P group, in the P region, and start counting there. 1, 2 from the S's, 3, 4, 5, as you move from left to right. If you end up at the noble gases and you've got more than 8, then you miscounted, because the noble gases have the octet. So you can't go any higher than that. Not with this rule. And that's what 3 is about. The maximum number of valence electrons in this scheme is 8. All right, so I did that one for you. How about phosphorus? Phosphorus is 1 to the left of oxygen in that group. It's the nitrogen, the pnictogen group, right? So it's going to lose one of these electrons, right? It's 1 to the left. So phosphorus is going to have 2 paired, these 2, and then these 3 are unpaired. The best way to know if you're pairing correctly is when you start filling these electrons in, go around one at a time, and then go around again, then you can start pairing. So you put the unpaired in first, and then you start pairing whatever's left over. Fluorine is 1 to the right of oxygen, so it's going to have 2, 4, 6, 7 rather than 6. Okay. That's just a restatement of the octet rule. And what I mentioned earlier, in the bonding process, atoms are tending toward acquiring an octet. That's the driving force in this theory, the driving force for the reaction. The atom is trying to obtain an octet. And when it does, if it does, it establishes for itself a noble gas electronic configuration, a complete octet. Okay. So I mentioned this earlier also. The ionic bond model requires that you form ions, a complete transfer of electrons. And in that process, you form either a negatively charged ion, which is an anion, or a positively charged ion, which is a cation. And the cations are going to be metals. The anions are going to be nonmetals. And remember, just a word warning, don't mess with the protons. If you change the number of protons, you've changed the element. So all of these processes are based purely upon gaining or losing electrons. Or in the case of covalent bonding, sharing those electrons. But the protons are there at this point just to identify the element. The number of protons says, this is my element. Nothing changes from that. Only the electrons. All right, there's some pretty pictures. I don't have time to stop here, so I'm going to skip over that. You can look at that at your leisure because you have access to the slides in Blackboard. Okay. So when potassium is in the first group, the alkali metals, so it loses only one electron, right? When you think about it, potassium has 19 protons, 19 electrons when it's neutral. So if you write the configuration, P6, 4s, 1. All right. So what are the valence electrons? The valence electrons are 1, just the 1. So think about it rationally. How is potassium going to attain a noble gas configuration with an octet in the outermost electron structure? Does it want to gain 7 electrons, right? Another S and then 6 more P's? It's very difficult to do that. It's hard enough just to change 1. The simplest way then is for potassium to lose that electron. Now the outermost shell has 8 in it. It has an octet now. And it looks like argon. Right? Argon would be like this. And argon would be up to that point, right there. Okay, so that's why potassium loses 1 electron rather than gaining any. About sulfur. Sulfur's on the other side of it's a nonmetal, right? And sulfur has 16. Right? So it's 1s2, 2s2, 2p6. Let's see. 3s2, 3p4. Let's see, 2, 4, 10, 16. Now, how does sulfur? Let's see, I need to keep track of people that are showing up late. Okay. How does sulfur obtain an octet? The simplest way for sulfur, rather than lose 6 electrons, it just gains 2. And that makes 3s2, 3p6. And now it also looks like argon. So you could form a compound between potassium and sulfur as long as potassium can lose an electron and sulfur can gain 2 electrons. So how would it do that? All right. Let's write the Lewis dot structure for potassium. and the Lewis dot structure for sulfur. 2, 4, 6. 2, 4, 6. Okay, we're good here, right? We can transfer an electron from here to here. Actually, that's probably a bad choice here. Let's do it this way. Let's just transfer that electron over here, okay? But sulfur needs another one, right? So we take this potassium and we transfer that one over here. Now potassium feels like it's argon, and sulfur feels like it's argon. And that's why the formula for that compound would be K2S, 2 potassiums, 1 sulfur. Okay. I think we've covered this in that discussion. How electrons are lost and how they're gained and why they do that. This just states it in black and white and blue, so you can go back and reference these slides at your leisure. All right. So these are guidelines, right? If the metal is in the first group, the alkali metals, it tends to lose 1 electron. That's why all of those metals have a +1 charge when they ionize, when they form a bond. In the second group, the alkaline earths, they have 2 s electrons that can be lost so that it can look like a noble gas. Magnesium is an example. It just loses 2 electrons, and that gives it a 2+ charge, right? If the deficit is 2 electrons lost, then you have an excess of 2 protons that are still there saying, I'm still magnesium. I'm just lost 2 electrons. So now I'm a magnesium ion. Aluminum is similar. It's in the third group over. It would lose 3 electrons in order to look like neon, and in the process become an aluminum ion. These are 3 examples of fixed charges, right? When these elements lose electrons so that they can bond and so that they can appear as noble gas configuration, they do that all the time, every time, by losing that many electrons for their particular group. Nonmetals, on the other hand, will gain electrons, right? Fluorine, which is a halogen, will always gain 1 electron. Oxygen, chalcogens, will always gain 2. Now remember, focus on this in terms of ionic bonding, right? When these elements are associating with metals, this is the way they do it. Fluorine gains an electron, oxygen gains 2 electrons, nitrogen gains 3 electrons. And all the members of its family do that. When they associate with metals, when you form a cation-anion association, that's the way they behave. Now, these nonmetals, when they bond with each other, it's a different story because they're not transferring electrons anymore. If 2 nonmetals bond, they bond by sharing, right? So then you have a different situation. The carbon group occupies a unique position, right? It's in the group 4, Roman numeral 4. So what happens is it can go either way. It can either gain 4 electrons or lose 4 electrons. Some of the hardest materials known, not as hard as diamond, but pretty hard, are carbides, right? Aluminum carbide is a very hard mineral that can be used in sandpaper. But just an example. But it does so, if it were to do that, this would be 3 plus, this would be 4 minus. So in that case, carbon has gained 4 electrons, and you would write it like this. Right? That's when it's in an ionic bonding situation. Okay, another concept that's useful is the isoelectronic species or series. And you can do these for yourself. All you need is for 2 or more ions to have the same electronic configuration. And the easiest way to do that is to recognize when they ionize, they assume a noble gas configuration. So they'll always have this octet, right? So when you form these ions, and they'll be neighbors to one another, like nitrogen to the right, then is oxygen, to the right is fluorine, right? They form their ions based upon their position. Fluorine only needs 1 electron. Oxygen needs 2 to look like a noble gas. Nitrogen needs 3. And they all have this electronic configuration, which looks like neon. Right? The same thing goes for these 3. As they lose electrons, they look like neon. These are isoelectronic series of atoms and ions. The only one that would be a neutral atom in this group, if it were there, would be neon. It doesn't need a charge because that is its neutral configuration. The rest of them, their configurations require ionization. Okay, I'm going to skip this one. In the interest of time, I'm going to have to skip this one too. All right, that's just an isoelectronic series, and all you have to do is start with some noble gas, and if you add an electron to it, and a proton to go with it, of course, then you move to the left. So we would go from argon, right? Argon, move to the left to make chlorine. It would have the same configuration as argon, but it would have a -1 charge. Move to the left another one, 2- charge for sulfur. Same electronic configuration as argon. Or you could move backwards. Take 1 away, and you get potassium. Take a 2 away, and you get calcium. Those are all isoelectronic. Okay. Let's see. I think I'm sliding off the... There we go. Get back in screen. Okay. I'm going to have to skip this one too. You can do this one. All you need to do is follow the periodic table, right? Get down to magnesium, which has 12 protons, 12 electrons when it's neutral. And then just follow it down from 1s, 2s, 2p. Magnesium is in the 3rd period, so, and it's in the 2nd group, so it's 3s, 2. So it should be B. Oops, sorry. I made a mistake. That's the neutral atom. This is the ion. See, when it says magnesium ion, right? I didn't even read my own sentence. So that makes magnesium look like a noble gas, as long as it has a 2+ charge. So when we form the ionic compound, you do it with a metal and a nonmetal. The metals lose electrons, the nonmetals gain electrons, and electrostatic charge brings them together and bonds them. Using the Lewis dot structure helps in understanding how that happens, right? Sodium only has 1 electron in its valence shell. Chlorine has 7, it needs 1. So it takes 1 from sodium. Now sodium looks like neon, and chlorine looks like argon. And that's what holds them together. Same thing is true for sodium bonding with oxygen. Now, in this case, oxygen requires an electron from one sodium, an electron from another sodium. So that's why Na2O is the chemical formula for that compound. Okay. When you form an ionic compound, the compound must be neutral. In other words, all charges must balance. So for sodium chloride, if you form this ion and this cation, that anion, you only need 1 of each to balance the charges. If you form something like this, then you do 2 of these to give you a 2- balancing a 2+. Okay, charges must balance, and you adjust the ratio when you're writing the compound. You adjust the ratio of ions so that the charge balances. Okay, so when you're writing a chemical formula, you need the symbol and you need the charge. When you're writing an ionic compound, you establish the charge based upon its position in the periodic table. Now, if the metal comes from the first group, the second group, or the third group, that is with boron, aluminum, so forth, they're always +1 for the first, +2 for the second, +3 for the third. Always. We'll talk about other charges in a minute. For the nonmetals that form the anions, you work from the right. So noble gases are not charged. Halogens, -1. Chalcogens, their next door neighbor, oxygen group, -2. Okay, lost my internet connection. Let's see. I'm gonna have to reshare the screen. Try to remember where I was. Hopefully the shared screen will remember PowerPoints. So let's do that again. Here we go. Share that. Yeah, there we go. I just need to start the slideshow again. Okay. Didn't lose too much time. When you write a compound, an ionic compound, and we're going to use this format as a jumping off point for writing covalent compounds as well. But for ionic compounds, it's simpler because the cation always comes first. That is, you write the metal first. And then you follow it with the anion. And there's a name for this. It's called a binary. compound. Now the authors, I'm not sure about your book, but in my chemistry books that I use at New River, the authors consider binary compounds only elements. That is, one element cation, one element anion. I think it's more useful to consider it cation on the left, anion on the right, and the cation can be a polyatomic ion, which I'll describe in a minute. The anion can be a polyatomic ion, but there's a pair, right? 1, 2, cation, anion. That's my binary definition. You don't show the charge. Now, I write the charge in there when I'm writing the compound just so I can get the balance right. But when you write the compound, you don't need the charge because the charge has been neutralized anyway. And you add subscripts for to add however many cations or anions you need to make the charge balance. And you make it the simplest ratio possible. In other words, if we were to write sodium chloride like that, that would balance the charges, right? You'd have 2 pluses and 2 minuses, but that's not the simplest ratio. Right? The simplest ratio is 1 and 1. So if you find yourself in that situation, reduce it to the simplest ratio. Other possibilities, this one, right? That's the simplest. You could have this and that, but that's not the simplest. Simplest whole number ratio. Okay. So in this case, we've got sodium, which is in the first group, has a +1 charge. Phosphorus is in the nitrogen group. It has a -3 charge. And just balance the charges. You need 3 positives to balance the 1 negative that has 3 -3 charge. So now the charges are balanced. Same here, right? 2 to 1, so you need two of the 1s to balance the 1 of the 2s. Now, what do you do when you have an odd and an even? It's what I call cross multiply. I borrowed that term from mathematics, right? So if this is a 2- charge, oxygen, you just put the 2 over by the iron. And the iron is a 3+ charge, you put the 3 over by the oxygen. And check yourself. 3 times 2- is -6, and 2 times 3+ is +6. We're balanced. So it works. This lead has a 4+ charge, and oxygen has a 2- charge, so you need 2 oxygens. Now we're getting into compounds that have transition metals. Now the transition metals are capable of multiple charges. Iron could be 3+ or it could be 4+. 2+, excuse me. 3+ or 2+, pardon me. Iron could be 4+ or 2+. And we'll talk about that when we name compounds, then I'll teach you how to deal with that change in charge. Okay. Ionic compounds tend to be solid. In fact, I can't think of a single liquid or gaseous ionic compound. Unless it's the formation of hydrogen bonded to one of the halogens. Like hydrogen fluoride, that's more covalent. Like I said before, it's a continuum, right? Ionic to covalent, somewhere in between. Hydrogen chloride, hydrogen bromide, those are gases, and they can be considered largely ionic. That's possible, yeah. Hydrogen sulfide. Everybody knows hydrogen sulfide is H2S. If you've ever been to Greenbrier County and driven close enough to one of the springs, they don't call them sulfur springs for nothing. The water that comes out of those springs is laced with hydrogen sulfide gas, well, compounds, and then it volatilizes, and there you go. You can smell it. But most ionic compounds are solids, and they don't form discrete units of cations and anions. They form a network. So for sodium chloride, you would have that and that surrounded by chlorides, and then you'd have sodiums stuck in here. So you form this ionic network. It just so happens that the simplest ratio of sodium to chlorine is 1 sodium and 1 chloride. Right? So we write this compound as NaCl and recognize that it's actually an ionic network. So this sodium is actually electrostatically attracted to 6 other chlorines, right? There are 4 here, and then there's 1 behind and 1 in front. But those chlorines also are attracted to 6 other sodiums. So it could be Na6Cl6, but the simplest ratio is NaCl. Okay, so they form this network. Notice that the chloride ions, and we say when we form an anion, we add IDE on the end. We just change the ending. But the sodium ions, we don't. We just say sodium. The metals, we just say what's the name of the element and then ion. The chlorines, with the nonmetals, we add the IDE on the end. All right, so notice the size difference. How did the chlorine get to be a chloride? It gained an electron. So its size expanded with that electron. Whereas the sodium ion lost an electron, it shrunk. So the relative size here, while it may not be exactly accurate, it's relatively accurate with the chlorides being larger than the sodium. So for the ionic compounds, instead of saying they're molecules, which they are not, we say formula units. Right? So the formula unit is the simplest whole number ratio of cations to anions. And that's how we write them. Right? You'll have this network, but the simplest formula unit is 1 to 1. Okay. So let's contrast. I think the next slide. Let me keep up with my hard copies here. Here we go. Well, stream of consciousness. The formula unit is used for ionic compounds because they are a network. And we have the formula unit is the simplest whole number ratio of cations to anions. The molecule, however, is covalently bonded. So its smallest unit does behave as an individual identifiable entity called a molecule. For instance, let's see, use a simple, this one. All right. The proper name for that is nitrogen monoxide. It forms covalent bond between the nitrogen and the oxygen, and it behaves as a single unit. So when you have nitrogen oxide in a container, it's going to be a gas, and all the other molecules are nitrogen monoxides. They interact, but they don't form strong bonds with each other. The bonding is between these two. Right? That makes it a molecule. It behaves independently. It has its own identity. So that would be a molecule unit in this multiple choice question. If the question were referencing covalent bonding, that would be a molecule unit. Okay, so these are the fixed charges for metals, right? Group 1 metals, the alkali metals, are always +1. Group 2s are always +2. Group 3s are always +3. They left boron out. I think boron can, it's a little squirrely. And I'm not going to throw boron at you. Not intentionally. Now, these transition metals are fixed charge. That is, those are the only charges that they have. But I'm going to allow for using the same convention that we use for transition metals and some of these other metals down here that can have multiple charges. And I'm referencing how we name compounds, and we'll get to that in just a minute. And I'll mention this again. But technically, these are fixed charges, right? Silver, cadmium, zinc. And of course, by this time, you should recognize those symbols and know their names because you've been memorizing them from the first day of class. All right, so we have binary compounds. Right, your authors do think that the binary compound is composed of 2 elements. I choose binary compounds are one cation, well, a cation and an anion. And their character can either be elements or they can be polyatomic. The ionic compounds are always metal, nonmetal. The covalent compounds are always nonmetal, nonmetal. All right, so now, how are we going to name compounds? There are 3 types. Type 1 compounds. Type 1 compounds are always metal, non-metal. Okay? Cation, anion. And they're named in that order. Cation first, anion second. The metal takes its ionic name directly from the name of the element. You just name the element. That's it. The anion, however, we suffix it, change the ending to IDE with some tweaks here and there for aesthetic purposes. What does it sound like? You know, if we said something like oxygen, if oxygen 2- were the anion, we wouldn't say oxygenide. We would say oxide. That just sounds better. So you just have to learn that difference. Okay, so type 1 compounds, metal, non-metal, the cation and the anion, and the metals are always fixed. Change that. The metals are always fixed charge. Right? They can only have one possible charge. So that means the group 1s, group 2s, group 3s, and those 3 transition metals that are fixed charge. They would fit into group 1. Now, what does that mean as far as naming goes? All that means is all you have to say in the name is, for example, group 1 and a halogen, right? Like that. We know how to write the compound, balance the charges, and then name it. You just name it sodium, and then chlorine becomes chloride. That's it. For type 1 compounds, that's all you have to say. What's the cation? What's the anion? And the overarching, the umbrella, the guiding principle for any writing compounds and naming compounds is non-ambiguity. What do I mean by that? I mean, when you see that name, there's only one way to write the compound. When you see the compound, there's only one way to write the name. There's no mistaking. You can't write it 2 or more different ways. And since we know that sodium can only have a +1 charge, and chloride can only have a -1 charge, then we know that from here to here is a definite step. No mistakes along the way. Another example. Say we have, let's see, this one. Right? Is that correct? Well, this is a 2- charge, and that's a 2+ charge. So yeah, 1 to 1. So we write magnesium oxide. And we're done. Type 1 compound. Fixed charge on the metal. That's the key. All right. These are just examples. Right? And you can figure those out for yourself. Those are type 1s. Notice that the metals are all fixed charge. Alkaline metal, alkaline earth, +1, +2, +2. Always. Type 2 compounds. Type 2s are metal, non-metal, just like type 1s. Only in this case, the metal is a variable charge. Now, that doesn't mean once you form the compound that the charge on the metal can change. That means the element could be 2 or more different charges. And then you form the compound with that charge and not the other. And the naming convention is the same, except you have to say what the charge is. Otherwise, you don't know when you look at the compound, or you don't know from the name how to write the compound. Now, if you have the compound, yeah, we'd say like this one. FeCl2. You know that Fe is iron, and you know that Cl would be an ion chloride. Right? So this one is always -1, right? So you can determine the charge of iron based upon the neutrality rule. This has 2 minuses that have to be balanced. If you've only got 1 iron, it has to be a 2+. So now you know the charge on the iron based on its formula. So now we would write iron charge in Roman numerals, chloride. Okay? Let's see. No, I thought we had another person coming in. or if you see the name written with a Roman numeral, you know it's a type 2 compound, or it should be. Sometimes they're written wrong, and you can determine that based upon where that metal comes from. So let's go the other direction. Say we have, let's see, how about this one? Cobalt II Oxide. How would we write that? Well, we need the symbol for cobalt. We need oxide. We know that oxygen is a 2-. And we know that cobalt is a 2+. Right? So 1 to 1 is all we need. They're balanced. What if we had Cobalt 3? In that case, now cobalt would be a 3+ charge. Now just checking, that's kosher. A 3+. Now you need to cross multiply. 6- 6+ balances. CH203. And I'll emphasize again, if you write cobalt like this, you're wrong. That is carbon monoxide. This is cobalt. Okay. So let's see. We went this direction. We went that direction. Okay. Type 2 compounds. The metal has variable charge. Okay. As you may have already guessed, we haven't talked about nonmetal. That's type 3. I need to get a new marker here. Type 3 compounds. Nonmetal. Okay. We've already mentioned earlier, well, these are other examples. Oh, before we get to type 3, excuse me. These are polyatomics. I took this table. This is the one that I distribute to my New River students. So this table, and there should be a copy of it in Blackboard also, a separate copy. But I wanted to put it here so be sure and talk about it. These are polyatomic ions. A polyatomic ion is one that has 2 or more elements bound together, and they're kind of like compounds, but they're ions. Right? They're bound covalently, very strongly, and the entire unit has a charge. For instance, let's take a carbonate. So notice that on the left-hand side, they're sorted by name. So you just follow down here, and there's carbonate, CO3 with a 2- charge. Over here, if you know CO3, 2-, then you follow it down this side, and there's CO3, 2-, and its name is carbonate. Right? So you have 2 ways, one side or the other, to find your polyatomic ion. So if we were to do this one and say, let's do this one, a type 1 compound. Calcium carbonate. Right? So we know that calcium is like this always, and carbonate is always a fixed charge too. These polyatomics, they don't change their charges. They're always the charge that's given in this table. Carbonate would be this, CO3, 2 minus. Okay, so that 2 minus balances this 2 plus, and that's the way you write the compound. CaCO3 is calcium carbonate. What if you have the formula? Let's say this one. Okay, I've done a lot of things at once here. One is, whenever you need more than one polyatomic, you have to use a parentheses. Because the charge doesn't belong to individual atoms. It belongs to the entire unit. So this phosphate, if you look it up on your chart, right, go down to phosphate down here, phosphate, PO4, 3 minus. So it's a 3 minus charge on the whole group. So you need 2 of them to balance this one. Right? So that's 6 plus, and this is 6 minus. So that's key. Whenever you need more than one polyatomic, you have to use a parentheses. Now, how do you know if you have a polyatomic? Well, one clue, it's not the only reason, but one clue is, if you've got 3 or more elements in your formula, and there's oxygen involved, it's a good bet that there's a polyatomic there. Now, there are some polyatomics that don't have oxygen, a few of them. Most of them do have oxygen. The only cation in that group, right? Notice they're all negative charges, except for one. The one cation in that group is ammonium. The rest of them are anions. Now, this is not an exhaustive list. These are just the most common and most often seen polyatomic ions. Right? So that's why they're in the list, because you need to be familiar with them. So let's see, ammonium is right here, right, NH4. And you can have ammonium bonded ionically with any one of these others. Right? So you could have a binary compound with 2 polyatomics in it. In our case, the cation will always be ammonium, but then the anion could be something else. But if you need more than one of those, you need a parentheses. All right. So you don't have to memorize these polyatomics. I know you're thinking that. You should have access to both the periodic table and the polyatomic ions in useful information in each one of the exam folders where you go to take your exam. The useful information should have this in there for the test that you're going to need it. And that'll be this one, the upcoming exam 2. If it's not available, it should be. If it's not, then it's okay for you to have this one in your possession when you take the exam, along with a periodic table. Always a periodic table. You can have a periodic table with you. Wow. Itchy nose. Okay. So these are examples of polyatomics. It says must be memorized. No, you don't have to memorize them. If you use them a lot, you'll just automatically memorize them. Okay, type 3s, 2 nonmetals. Right? Now, nonmetals are not going to form ions. Right? These are covalent compounds, but we're going to use the convention that we started with ionic bonding to name the type 3 compounds. So if you got 2 nonmetals, first question is, which one comes first, right? Usually, the one to the left will come first. So if you have nitrogen and oxygen, right? Nitrogen is to the left. It goes first. NO, nitrogen, and you just say, how many are there? There's one nitrogen, but for the metal, we never say mono. And you use prefixes, right, to name them, right? If there's one of them, it's mono. If there's two of them, it's di, right? I think we've got that. Yeah, it's in the next slide, right here. There you go. So these are Greek prefixes. Mono is 1, di is 2, tri is 3, tetra 4, on down to 10. Deca is 10. Those are the only ones that you need to memorize. You do need to memorize these. So we go back. Now if we're going to name this, we just say nitrogen. And then how many oxygens are there? 1. And for aesthetic purposes, we don't say monoxide. We don't have two O's together. Monoxide. If we had 2 oxygens, right, we would say dioxide, or the infamous global warming compound, carbon dioxide. Okay, so that's the way you name type 3 compounds. You just say, how many are there of each one? Carbon dioxide, we've mentioned that before. Sulfur hexafluoride. Dinitrogen, now we have 2 nitrogens, so you do say dinitrogen tetroxide. That's it. We're done. So in many respects, type 3 is the simpler of the conventions. You don't have to balance charges. You just have to say how many there are. And this is like a decision tree. If there's a metal present in the compound, then it's either a type 1 or a type 2. If they're both nonmetals, then you're automatically type 3. If it's one of these, then you have to decide, is the metal fixed charge or variable charge? If it's variable charge, then you go to type 2. And you have to use a Roman numeral to say what the charge is. So it's really very simple. You just need practice. Okay, polyatomic ions. I don't think we need a separate decision tree. For polyatomics, you just look at the metal. If there's only one polyatomic in there and it's got a metal, then we know that the polyatomic is an anion. You just be sure that you have the polyatomic written correctly, correct charge, and is it a type 1 or a type 2 with the metal? And then, if it's a type 2, you have to say what the charge is. If you're going to write the compound and you need more than one polyatomic, you better use a parentheses. Okay, now there's a convention for naming acids. And the reason for that is it's inherited from the medieval times, from the alchemists. And what we've done for modern chemistry is to standardize it, the naming convention. Okay, so when you are looking at a compound, how do you know it's an acid? Well, if it was written correctly, the first element in the acid is hydrogen. There may be one of them, there may be 2, it could be 3. I've never seen 4, 1, 2, or 3. So we would have that, or we would have that, or we would have that. Okay. Then you follow it with the rest of the name. The rest of the name could either have oxygen or no oxygen. So in our example there's no oxygen. When there's no oxygen, let me see if I'm jumping ahead of myself. Hold on. Yeah, let's go to the next one. When there's no oxygen, you start the name with hydro, referencing the H, right? Hydro. Then you go to the second part, basically the anion side, because when you put it in water, actually, before you put it in water, it's not an acid. It has to be in water. So right now, it would be hydrogen chloride. And actually, it's a gas. If it's pure hydrogen chloride, it's not an acid. If you put it in solution, and we use AQ to mean aqueous solution, now it's an acid. Why? Because now that hydrogen can dissociate from the molecule and attach itself to water molecules. We'll talk about that in another chapter. But if it's aqueous, then you say hydro, and then you say, all right, if it's hydrogen chloride out of water, in water, the ide becomes ic. Hydrochloric acid. Okay. All right, that's for any acid that has no oxygen in the molecule. The next example they've given is HCN. CN is a polyatomic ion, cyanide. So cyanide becomes ic, cyanic, hydrocyanic acid. H2S. S is hydrogen sulfide, would be the gas. Put it in water, and you get hydrogen, or you get hydro, and then S, sulfide. And here's another change. Rather than sulfic, just doesn't sound right, we say sulfuric, hydrosulfuric acid. So what if there is oxygen in the molecule? If there's oxygen in the anion side, which means it's automatically a polyatomic, right? If there's oxygen there, then you don't say hydro. You go to the anion side and work from there. So, example, H2SO4. Okay, that SO4 is sulfate. So if this is sulfate, and we don't say hydro, you start from sulfate, 8s become X. So you just say sulfuric acid. And you're done. If you're working backwards, then you look at sulfuric and you say it ends here.
Watch. Pick your feet up, buddy.
Oh, okay. Never mind. You look at the ic and you say, okay, that had to come from 8. Sulfate was the origin. So now you go back to sulfate, which is SO4, 2 minus, and you need hydrogens to balance the charge. In this case, hydrogens are always positive. In fact, unless it's deuterium or tritium, it's only got 1 proton anyway. So if it's the vast majority of hydrogens in nature, it's one proton, one electron. So this is usually the same as that. It's just a proton. Now, of course, if it's deuterium, if it's like this, but if it's like this, then it's not that. It's got a neutron in there too. But most of the time, it's okay to refer to it as a proton. So it's got two positive protons, which balances the two minus. That's how you write backwards. Now, if we have this, like that, that is sulfite. And ites become us. So in that case, we would say sulfurous acid. Okay? I know I'm going to run out of time, but I got to cover this stuff thoroughly. There's another decision tree. Which one of these is written incorrectly? Well, look, what do you have here? Type 1, type 2, or type 3? Potassium is a fixed charge, so it's a type 1. You only have to say potassium. And then NO3 is a polyatomic ion, which is nitrate. Potassium nitrate, you're done. How about this one? Titanium oxide. Well, titanium is a transition metal. So it has more than one possible charge. What is the charge? If this is written correctly, that means 2 times 2 minus for oxygen means 4 minus. Titanium has to be a 4 plus. So that's written incorrectly. This needs to be a Roman numeral 4. Okay, let's skip down here. PBr5. Both of those are nonmetals. That's a type 3. So in that case, you only have to say how many there are. Phosphorus, penta for 5, bromide, and you're done. This one is a type 1 compound because calcium is an alkaline earth, 2 plus charge. Chromate, CrO4, see, 1, 2, 3 elements, and one of them's oxygen. So you look for this one and see, oh yeah, it's a polyatomic. It has a 2 minus charge. It balances calcium with a 2 plus charge. Calcium, chromate is it. You're done. Okay. Let's see. We talked about polyatomic ions already. Most polyatomics have a negative charge. Ammonium, for our purposes, is the only one in that table that has a positive 1 charge. Hydronium is another case. That one forms in acids, and we'll talk about that later. It's not one that you normally see bound to anions. Most of the polyatomic ions contain oxygen. Some of them don't. Cyanide's one example. These two actually end their naming in IDE already. So if we have an acid with cyanide, okay, let's try this one. All right, no oxygen, so we start it with hydro. Cyanide, the I becomes ic. Hydrocyanic acid. Okay. Let's see. There are some, one in particular, of the polyatomics that has two types of hydrogens in it. The acetate ion. When you form an acid with that one, you add one out here. That hydrogen is a different nature than this hydrogen. These hydrogens are bound into the polyatomic ion. They do not dissociate in aqueous solution. That one does. That's why, well, if this is acetate and there's an oxygen, we say 8 becomes ic, acetic acid. Okay? Acetic acid is, if it's 5% concentration, it's vinegar. Okay. All right, I already said that. That's nothing new. I'm going to have to skip this one too. That looks like we did that one already. Okay. So when you combine ammonium and carbonate, how would you write that? Ammonium and carbonate, right? That one has a +1 charge for that whole group. This one has a -2 charge for that whole group. You need 2 of these positives. You have to do a parentheses. Now you have 2 positives against 2 negatives, and you're balanced. All right? Oh, concept question. Maybe we have time to go through some of these because it's only 10:36. I was moving pretty fast. I have to apologize for that. I generally take longer and just ease my way through the material, but I'm forced by a pending meeting to get done on time today. Okay, let's see. After pasting a soft, lustrous, malleable material in a container of yellowish gas. Okay, what are we talking about there? Lustrous, malleable, that's a metal, right? That's a metallic characteristic. And we put it in a yellowish gas. There are no metals that are gases. There's one that's a liquid, but there are no gases. So this has to be a non-metal. A violent reaction occurs, and a white crystalline material, okay? So you've got a metal and a non-metal reacting, and they form an ionic compound, which is a white crystalline substance. So we've changed the nature of the substances from this one and that one to this one. So you decide that maybe it's safe to taste it. Right? What do they say? Chemistry is like cooking, only you can't lick the spoon. And it tastes salty. All right. Is there not enough information? I think we've got enough information to figure out what it is. Let's see. The 2 materials are likely to be the elements sodium and chlorine reacting to share electrons to produce molecular compound sodium chloride. Okay, the key word there that's wrong is share. They do not share electrons. One takes electrons from the other. The 2 materials are probably sodium and chlorine. Okay, yeah. Both reacting by a transfer of electrons produce the ionic compound. There you go. 2 materials are homogeneous compounds reacting to produce, no. C is the best answer. Okay, we want to fill in this table, right? There's a 1, there's a 2, there's a 3, and there's a 4. So the 1 and the 2 are going to be names of those compounds, and the 3 and the 4 are going to be formulas from the names. So let's see what we got here. Sodium, make room. So here's one, and that's written like this. Now we need to name it. Okay. So what do we have? Well, we've got a metal that's a fixed charge, sodium. We know it's a type 1 compound because of that. And this HCO3, you've got an oxygen in there with some other elements, so it's probably polyatomic. So you look it up, and it turns out to be hydrogen carbonate. We used to call it bicarbonate. And that's it, because this is a +1, that's a -1. Sodium hydrogen carbonate, or sodium bicarbonate, which is baking soda. All right, how about the other one? Let's do 2. So we've got this formula. Type 1, type 2, because that's a metal. It's still type 1. So we say magnesium. Hydrogen carbonate. Okay? How about 3? We'll put 3 over here. As long as I'm still on, it's shifting a little bit, isn't it? There we go. 3. Sodium phosphate. All right, we know we have sodium, and we know it's a type 1 compound because sodium is an alkali metal. It's in group 1. Sodium. Phosphate is a polyatomic ion, right? And you should know that because there's no element in the periodic table that says phosphate. There's a phosphorus. But if phosphorus were there, it would be phosphide. Phosphate is a polyatomic. And you look it up. What is phosphate? Phosphate is PO4, 3- charge. Sodium is a fixed charge there. So we need 3 of these to balance those 3 minuses. Right? 4. Magnesium phosphate. Magnesium phosphate would be magnesium, right? Type 1 compound. Phosphate's the same one, PO4, 3-, but this is a 2+, right? So in this case, you would cross multiply. So you bring the 3 over here, and with parentheses, the 2 over there. So 2 times 3- is 6-, 3 times 2+ is 6+. We're balanced. And that means B is the answer to this concept question. Let's see, they usually only have 2. Yeah, we're done. So I'll stop the share. Okay. Let's see. What's next? Next time we meet, we'll do chapter 5. And then we'll follow the next week, we'll do chapter 6. And then after that, we'll have a review for all of it. Okay? I got a few more minutes if anybody has questions.